Supermassive black holes do not move. For 50 years, that was the one thing every model agreed on. They sit at the gravitational bottom of a galaxy, and they stay there. Then the Hubble Space Telescope caught a needle of light 200,000 light-years long, twice the width of the Milky Way, pointing straight out of a small galaxy 8 billion light-years away. In December, the James Webb Space Telescope measured a wall of gas at its tip. This is the story of RBH1 and of two expert teams, reading identical data and reaching opposite conclusions. In 2022, a team led by Peter van Dokkum of Yale University was pointing the Hubble Space Telescope at something unrelated to black holes. They were studying dwarf galaxies that appeared to contain almost no dark matter, which is its own strange problem. One of the images came back with something extra in it. Running out of the center of a small, compact star-forming galaxy was a line, not a smear, not a streak of noise, a needle. Almost perfectly straight, extraordinarily thin, and long enough to dominate the frame. Nothing in the catalogue looked like it. When an image contains something you have never seen before, only two questions matter, and they have to be answered in order. Is it real? And how far away is it? The first is easier. A cosmic ray strike shows up in one exposure and not the next. A processing artifact appears at one wavelength and vanishes at another. The line appeared in multiple images, at different times, in different filters. Whatever it was out there. The second question is where this story begins. An image is a flattening, so a nearby star and an object halfway across the observable universe land on the same plate with no depth information at all. The line could have been small and close. It could have been enormous and impossibly distant. It was the second one. And that is when it stopped being a curiosity and became a problem. To understand why, you have to understand what we thought we knew about supermassive black holes. They are the anchors, millions to billions of times the mass of the Sun, compressed into a volume smaller than our solar system, sitting motionless at the gravitational bottom of a galaxy. The link is so reliable, astronomers use it as a measuring tool. The black hole's mass tracks the mass of the galaxy's central bulge along a tight relation calibrated by Shooter, Rain, and Green. Show an astronomer the bulge, and they will tell you the black hole. They are the last thing in the universe you would expect to find wandering. But there was a loophole, and it is old. Work stretching back to Bonner and Rotenberg in 1961, Bakenstein in 1973, and later Gonzalez, Campanelli, Lusto, and Zlokawa established something counterintuitive. When two black holes spiral together and merge, the gravitational waves they release do not radiate evenly in all directions. The final burst is lopsided. It carries away net momentum in one direction, and the merged black hole recoils the other way. Simulations show that when the two spins are steeply misaligned with the orbit, that recoil can exceed 5,000 kilometers per second. There is no galaxy in the universe with an escape velocity that high. There was a second route as well. Bring three galaxies together in quick succession, and the standard outcome of a three-body encounter is that two black holes bind tighter, and the third gets thrown out. Both routes fall out of galaxy mergers naturally, because when galaxies merge, their black holes always end up in the same place. The theory was not exotic. It was close to unavoidable, and in 50 years of looking, nobody had ever found one. A confident prediction, half a century old, with an empty evidence column underneath it. Measuring the distance to something like this means taking its light apart. Elements do not glow smoothly across a spectrum. Hydrogen glows at specific wavelengths, oxygen at others, nitrogen and sulfur at others still, and the pattern of spikes they leave is a fingerprint. The universe is expanding, so as light crosses it, that whole pattern gets stretched toward the red. Measure how far it has slid, and you know how long the light has been in transit. The team took a spectrum with the low-resolution imaging spectrometer on the Keck telescope in Hawaii. Both the line and the compact galaxy at one end of it came back at the same redshift, 0.964. The light left roughly 7.5 to 8 billion years ago, before the Earth had formed, before the Sun had condensed out of its own cloud. That matters twice. Because the two sit at the same distance, this is not a chance alignment. They are physically connected, and distance turns the angle it spans on the sky into a real length. 62 kiloparsecs, about 202,000 light-years end to end. The Milky Way's disk of stars is roughly 100,000 light-years across. This single filament is twice that, and it is only 3,000 or 4,000 light-years thick, 60 times longer than it is wide, and straight along nearly its whole run. The team then looked at the light itself section by section. They measured the ratio of oxygen emission to hydrogen emission along the feature. The logic is simple. It takes considerably more energy to make oxygen glow than hydrogen, so a quiet galaxy is brighter in hydrogen. Flip that ratio, and something energetic is dumping power into the gas. A violent burst of star formation, a supernova, a fast shock, or material spiraling into a feeding black hole. Along this feature, the oxygen-to-hydrogen ratio varied from roughly 1 to 10, a mixture of ordinary star formation at one end and fast shocks at the other, terminating in a bright knot of glowing oxygen. Then they looked at the colours of the starlight and found the detail that made the case. The colours change systematically along the line, fitting a model in which stellar age increases steadily with distance from the tip. Young stars at the bright end, progressively older stars moving back towards the galaxy. Think about what a one-directional age gradient means. A galaxy has no reason to build its stars in sequence from one edge to the other. A trail does. A trail is made in order by something moving, and the gradient tells you which way it went. Fitting it gave a time since ejection of about 39 million years, and an implied velocity of roughly 1,600 kilometers per second. In 2023, Van Dokkum and his colleagues published in the Astrophysical Journal Letters, the first strong candidate for a supermassive black hole thrown out of its own galaxy, ploughing through intergalactic gas and igniting stars behind it. The excitement lasted about 2 months. The objection came from the Instituto de Astrofísica de Canarias, from a team led by Jorge Sánchez Almeida with Mireia Montes and Ignacio Trujillo. It was not a vague complaint. It was quantitative, and it went straight at the weakest joint in the argument. Their point was energy. A supermassive black hole passing through the thin gas outside a galaxy is a small disturbance in a very sparse medium. For that disturbance to trigger gravitational collapse and build 3 billion solar masses of new stars in only 39 million years, the gas would have to be in a genuinely exceptional condition to begin with. Their alternative required nothing exceptional at all. What if it is just a galaxy? Specifically, a bulgeless disk galaxy, a flat, thin spiral with no central bulge, lying exactly edge-on to our line of sight, so we are looking at it down the plane of its own disk. Those galaxies exist. They are not rare. Then they produce 3 pieces of evidence. First, the velocities. Measure how the gas velocity changes along the structure, and it does not look like a wake. It looks like a rotation curve. One side approaching, one side receding, with a maximum rotation velocity around 110 kilometers per second. The signature of a spinning disk viewed edge-on. Second, plot that rotation velocity against the object's stellar mass, and it lands directly on the Tully-Fisher relation, the tight correlation obeyed by disk galaxies. A trail of stars scattered behind a moving black hole has no reason to sit on that line. Third, they compared it to IC 5249, a nearby bulgeless edge-on galaxy. The rotation curve matched, the stellar mass matched, the extent, the thickness, the surface brightness profile, all of it matched. Sanchez Almeida put it plainly. The motions, the size, and the quantity of stars fit what has been seen in galaxies within the local universe. It is a relief, he said, to have found the solution, because the new scenario is much simpler. Then he added something that tells you how honest this argument has been from the start. In one sense, he said, it is also a pity, because fleeing black holes are expected, and this could have been the first one ever observed. In 2024, the Canary Islands team pressed harder, and this time they went looking for absences. Montes, Sanchez Almeida, and Trujillo obtained new, extremely long exposure Hubble imaging and aimed it at the two features the runaway model absolutely requires. The first is a bow shock. A black hole moving supersonically through gas must be piling that gas up in front of itself, the way water stacks at the prow of a boat. There should be a visible structure at the head of the line. The second is a counterwake. In the ejection scenario the Discovery team favoured, the black hole was not thrown out alone. A second binary black hole should have gone the opposite way at the same moment, carving a fainter mirror image trail. Neither appeared. The new images went fainter than anything before and found no bow shock and no counterwake. Exactly what you would expect if there had never been a black hole there at all. At that point, the argument looked settled, tilting towards the boring answer. Then the largest telescope ever launched turned toward it. The instrument that changed everything is Webb's near-infrared spectrograph, operating in integral field mode. An ordinary spectrograph takes light from one place and spreads it into a spectrum. An integral field unit takes a small patch of sky and records a full spectrum at every point across it at once. What comes out is a cube, two spatial dimensions with wavelength as the third, which means you can map the velocity of the gas across the object point by point. Van Dokkum's team pointed it at the tip. In December of 2025, they published what they found. Across a distance of 1/10 of an arc a second, about 1 kiloparsec, roughly 3,000 light-years, the radial velocity of the gas changes by approximately 600 kilometers per second. Not a gradient, a discontinuity, a wall. 600 kilometers per second is over 1.3 million miles an hour, and it happens across a single step. Rotating disks do not do that. Rotation curves rise and fall smoothly because the gas is orbiting under gravity in an ordered way. A jump that large over that distance is the signature of a shock front. Gas slammed into and compressed by something moving faster than the local speed of sound. The team fit a shock compression model to the geometry and pulled out two numbers. The object producing the shock is moving at 954 kilometers per second, give or take about 100, at an angle of 29 degrees to our line of sight. That is a little over 2 million miles an hour, 0.3% of the speed of light. At that speed, an object would cross the United States coast to coast in roughly 4 seconds, and circle the Earth in 42. Conserving energy over the lifetime of the wake gives it a mass of at least 10 million times the Sun, several times heavier than the black hole at the center of our own galaxy. The evidence for a supersonic bow shock at the head of this object, the paper says, is very strong, bordering on overwhelming. Van Dokkum said it more plainly still. With Webb, he said, they discovered the huge displacement of gas at the tip of the wake, where the black hole is pushing against it. The shock signatures are crystal clear, and there is just no doubt about what is happening here. Then the team did something worth noticing. In the note attached to their own paper, they stated that the original discovery paper was right about the key interpretation, but had quite a few details wrong. The velocity came down from 1,600 kilometers per second to 954. The age of the trail went up from 39 million years to roughly 70 million. 70 million years ago, on Earth, the dinosaurs were still alive. Picture standing there. Not on the black hole, nothing stands on a black hole, but out ahead of it, in the gas it is about to reach. The first thing you would notice is how little there is. The gas outside a galaxy is roughly 1 particle per litre of space, a vacuum better than anything ever manufactured on Earth. No wind, no sound, no sensation. The galaxy it belongs to would be a smudge somewhere behind you, 200,000 light-years away. Then the shock arrives. You would not see the black hole. There is nothing to see. No surface, no glow, only a region where light stops coming back. Out here almost no material falls into it, so there is no accretion disk, no X-ray beacon, none of the fireworks that make black holes visible near galactic centers. It is genuinely dark. What you would see is the gas in front of it lighting up. Hydrogen and oxygen slammed hard enough to glow, piling into a curved sheet sweeping past at 2 million miles an hour. And behind it, gas squeezed past the point of no return collapses under its own weight, and new stars ignite in the dark, one after another, marking the path of something you cannot see. That is the picture the Discovery team is defending. 200,000 light-years of newborn stars laid down like a contrail by an object smaller than our solar system. And that is the picture the other team says is not there. In February of 2026, the Canary Islands group published again. Sanchez Almeida, Trujillo, Sebastián Sánchez, and Montes. And this time they were not arguing from different observations. They were arguing from the Webb data itself. Their tool was the standard classification diagram used across extragalactic astronomy, plotting the ratio of ionized oxygen to hydrogen against the ratios of nitrogen and sulfur to hydrogen. Different physical processes occupy different, well-mapped territories on that plot. Ordinary star-forming regions sit in one zone. Gas excited by fast shocks in merging galaxies sits somewhere else. Gas heated by a feeding black hole sits somewhere else again. They took the Webb line ratios measured at the tip, the exact place where a bow shock should be, and plotted them. The points landed on the locus of low metallicity, low extinction hydrogen regions. Ordinary glowing nebulae, the kind found in any star-forming galaxy. And that region of the diagram, they noted, does not overlap with the territory typical of shocks in merging galaxies. Their conclusion from the same data cube: the structure is a star-forming galaxy, and the bright knot at the end is one of its nebulae. So here is where things stand. The tip of this object is either a bow shock generated by a supermassive black hole travelling at 2 million miles an hour, or a cool cloud of gas where stars are being born. Two expert teams, the finest data ever collected on it, and diametrically opposed readings, not of different evidence, but of the same evidence. That is not a failure of science. It is what the edge of the measurable looks like, up close, before it resolves. While the observers argued, a theory group took the measured velocity at face value and ran it backwards to reconstruct the black holes that would have had to merge to produce it. Tausif Islam at the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara, with Tejaswi Venumadav and Digvijay Wadekar, published in January of 2026. They generated 500,000 possible black hole pairings, pushed each through 3 independent models of gravitational wave recoil, and asked which could actually produce a kick of 954 kilometers per second. Almost none of them. 2 black holes with no spin at all. Maximum recoil around 180 kilometers per second, 5 times too slow. Spins aligned with the orbit, about 200. Spins anti-aligned, about 300. Spins misaligned and precessing, but the two black holes very different in mass. Still peaks around 200. Only one configuration survives. The progenitor had to be two black holes of roughly comparable mass, a ratio near 3:1, with their spin axes strongly tilted relative to the orbit, and the larger of the two spinning at close to the theoretical maximum. Their best estimate for that spin is around 0.8, on a scale where 1 is the fastest a black hole can rotate. That carries its own implication. You cannot spin a supermassive black hole up that far through chaotic feeding, or a series of small mergers. Those add angular momentum in random directions and largely cancel. You need sustained, coherent accretion from a single organized disk over a long time. So the galaxy this thing came from was almost certainly built in a major gas-rich merger between two galaxies of comparable size. One more number stays with you. Had the LISA gravitational wave observatory been operating when those two black holes finally merged 70 million years ago, the signal would have arrived with a signal-to-noise ratio somewhere between 1,000 and 2,000. It would have been among the loudest events ever recorded, and there was nothing here to hear it. There is a second thread to this, and it arrived from a completely different direction. At the University of Maryland, Robert Stein, Suvigi Jari, and their colleagues built a machine learning search and turned it loose on data from the Zwicky Transient Facility at Palomar Observatory, whose telescopes scan the northern sky every 2 days, looking for things that flare. What they were hunting are tidal disruption events, the burst of light released when a black hole tears apart a star that wandered too close. In November of 2025, the search found one that was wrong. It did not go off at the center of its galaxy, where essentially all of them do. It went off about 30,000 light-years out, roughly the distance from our Sun to the center of the Milky Way. The flare's shape and color gave the mass of the object behind it, about 1 million times the mass of the Sun. Before the flare, there was nothing there. No emission at that position in any archival image, no companion galaxy, no hint of anything. As Stein put it, you would not have suspected a black hole was hiding there. His team suspects this one sits at the core of a faint dwarf galaxy, being pulled apart into the larger one, rather than being a recoil ejection. But Van Dockum drew the connection himself, and it is why this belongs in the same story. The relation between the two black holes, he said, is that in both cases we are left with a massive black hole in empty space, which is very cool. Whichever way the argument about that line resolves, an independent method has now found a supermassive black hole far outside any galactic center, invisible, in a place nobody had thought to look. Both teams agree on how this ends, not with a better argument about one object, with more objects. Hubble found this thing by accident, and the reason is a number worth sitting with. In more than 35 years of operation, everything Hubble has ever imaged adds up to well under 1% of the sky. It sees far and sharply through a keyhole. If these structures are even moderately rare, we have been looking at almost none of the places they could be. On the 30th of August, 2026, 18 days from now, a Falcon Heavy is scheduled to lift off from Launch Complex 39A, carrying the Nancy Grace Roman Space Telescope. Its launch moved up by roughly 8 months. It carries a mirror the same size as Hubble's and a field of view about 100 times wider, and it will survey a substantial fraction of the entire sky at Hubble's resolution and sensitivity. Van Dockum's team names Roman and Euclid explicitly in their conclusions as the datasets that will settle this. Stein's group is pointing at the Vera Rubin Observatory, which has just begun its 10-year record of the changing sky. Both turn a fight over one object into a question about a population, and a population has properties a single object never can. Enough examples, and the boundaries on those classification diagrams get redrawn honestly instead of argued over. Here is what I keep returning to. Every route to a runaway supermassive black hole runs through a galaxy merger, and mergers are how galaxies grow. Our own is on a collision course with Andromeda. Both have supermassive black holes at their centres. Whatever that line turns out to be, the mechanism is not exotic. It is the ordinary end state of the ordinary process by which the universe assembles itself. We told ourselves supermassive black holes are the fixed points of the cosmos, the one thing that stays put. Something resembling the opposite has now been photographed by the two most powerful telescopes ever flown, analysed by two expert teams using identical data, and declared by each of them to be two completely different objects. The disagreement is the honest part. What both readings leave standing is the unsettling part. Black holes with millions of times the Sun's mass, sitting in the dark far outside any galaxy, visible only in the accidental moment when they happen to run into something. We found one by pointing a telescope at the wrong thing. Thanks for watching, and I'll see you in the next one.